Welcome back. So now we're going to do two problems that are in your notes, and we're looking at congruence transformations. All right, so we're going to use the definition of congruence in terms of rigid motions to determine whether the two figures are congruent and explain your answer. All right, so here we're trying to prove using rigid motions if triangle ABC is congruent to triangle DEF. Well, I don't think it's any stretch to realize that triangle ABC and triangle DEF have different sizes. We could just compare one side, right? So BC here is 4, and EF is 1, 2, 3, 4, 5, 6, 7, 8. Right? They're not the same size. Since rigid motions preserve distance, there's no sequence of rigid motions that will map triangle ABC to triangle DEF. Right? No rigid motion is going to change the size. Therefore, triangle ABC is, this is the symbol for not congruent. We'll write that underneath on your notes here. This means not congruent. We crossed it off. Congruent, oops. Nope, not congruent. There we go. Is not congruent to triangle DEF. All right, so let's try the second one, since those weren't even congruent. You can map you can map figure JKLM to PQRS by the translation that has the following coordinate notation. Now, how would we know it's a translation? Has to be a translation because it has they have the same orientation, right? The two figures have the same orientation, they're facing the same direction, has to be a translation. So let's find the translation. So we're going to check all of our vertices. All right, so for J here, J is moving to P, right, because those two letters are first. Right, so we go 1, 2, 3, 4, 5 to the right, and 1, 2, 3 up. All right, so I'm just going to put a little vector there. 5, 3, because I didn't want to put dots everywhere. All right, let's check now K and Q. All right, 1, 2, 3, 4, 5 to the right, 1, 2, 3 up. All right, also the same vector. And then let's check L and R. All right, so 1, 2, 3, 4, 5 to the right, 1, 2, 3 up. So far, so good. Oops, a little quicker there. And then M to S, 1, 2, 3, 4, 5 to the right, 1, 2, 3 up. So notice everybody went the same direction and the same distance. So our translation, every point on our figure has gone 5 to the right, so it's x plus 5, and 3 up, x plus 3. A translation is a rigid motion. Right? Remember, rigid motions are isometries. They preserve congruence. Actually, let's write the whole sentence there that I wanted to say. Rigid motions preserve congruence. And we'll use the symbol for congruence. We'll make it a little easier on ourselves. Rigid motions preserve congruence. Therefore, JKLM is congruent to PQRS. So you see we're using our transformations to show that our figures are congruent by finding a sequence of transformations that maps one figure to the other. The definition, and actually this should be in your notes, I know the whole page is in your notes, is the bottom part in your notes. It is not. So I want you to add this to your notes, but not the whole thing. Actually, you know what? Since you have the definition in your notes, right? That two figures are congruent if one can be tamed by the other by rigid motions, right? I'm going to have you just write part of it. So I'm going to have you write just the underlined parts. Add that to your notes. Definition of congruence and There must be some sequence of rigid motions that maps one to the other. All right, so just add that part to your notes. There's enough room, I think, at the bottom of that. And you can take a little bit of the top of the next box to fit that in. So definition of congruence, must be some sequence of rigid motions that maps one to the other. Let's look at one more problem. Oh, and by the way, if you didn't have time to write that down, just pause me. Although it's taking so long to change the page, you might have time to write that down without even pausing me. Here we go. All right, so this one is also in your notes. Yes, it is. All right, so for each pair of congruent figures, we want to find the sequence of rigid motions that maps one to the other. All right, so here, this one is, it's got to, they're not facing the same way, right? So it's got to be a reflection or a rotation involved in our sequence of transformations. Right? So this one is not a single transformation. It's going to take a composite transformation. Right? And one of them is a reflection. Notice that they are mirror images of one another. So RST and ABC are mirror images of one another. They're just not facing one another because one of them has been moved. So we can map triangle ABC to triangle RST by a reflection followed by a translation. Provide the coordinate notation for each. We're going to write reflection in words as well as the correct coordinate notation, and we're going to draw it in to help us out. All right, so reflection, I think you can see what we're going to reflect over. We're going to reflect over the y-axis. And then let's add the coordinate notation. That would be, remember that's an R, y-axis, right? And that's going to change all of our points so that the x becomes the opposite, but the y stays the same. So I want you to add both in there, words and coordinate notation. So let's draw the figure in. So it's going to be 1, 2, 3 right here would be S. And then R, 1, 2, so S is 4, or R is 4 away, so it's going to be right here. And T didn't move at all because it's on the line of reflection. And I think my figure looks a little crooked. Let's see if I can make it straighter. I bet yours looks better than mine does. No, oh well. Actually, you know what? I'm so embarrassed by that figure. Let me try it just a little bit better. Okay. I'll take it. All right, so this is S prime, and this is R prime. All right, so if I reflect it, right, I get that figure there, R prime, S prime, T prime. If I want to map it to triangle ABC, notice how I have to translate. 1, 2, 3, 4, 5 units up, right? Each of these has to move 5 units up, and we could do that for all of them. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. All of them have to be moved up 5 units. That effect, maybe we'll put the vectors in there. And this one. So all being moved the exact same direction and distance. So our translation in coordinate notation, every point is going to move, oops, nothing horizontally, but 5 up. All right, so that T stands for translation. X, Y says we're going to do the same thing to all our points. We're not going to change the X at all, but we're going to make the Y's 5 more. All right, and so now let's look at the last one here. And so actually, let's also write in one other thing right underneath it. Because there is a sequence of transformations that maps one figure to the other, we can say that triangle ABC is congruent to triangle RST. That's that in our congruent statement. Now let's do the second one. You can map triangle DEF to triangle HJK by a rotation followed by a translation. Let's rotate around the origin, because that's easier. It's easier to put in coordinate notation. Matter of fact, it's pretty much impossible to put it in coordinate notation if we're not rotating around the origin. All right, so we're mapping DFG to HJK. So we need to move DFG to DHK. So now let's, for this one, the reflection was easy, right? We just had to make all of the y coordinates, the x coordinates the opposite. But for the rotation, let's write down our coordinates. I think that'll help us. So J is located at -1, 5. K, and actually, in theory, I actually always write down my matrix to help me out when I'm doing the transformations and to keep track of things. Right? You can be much more accurate when you do that. But let's definitely do it, though, for the rotation. All right, so we have -1, 5 for J. K is at, oh, I guess I should put H first, huh? And actually, excuse me, it was DFG we were, well, let's just start all over again. Sorry, DFG. I just happened to notice the other figure first, but that's not the one that's being mapped. It's DFG. And D is at 2, 1. Oops. What the heck happened to my 1 there? I think that was supposed to be the bottom part of my 2. F is at 4, 1. There we go. And G is at 2, 5. All right, so on a rotation, we flip the x and the y, right? So it's going to be yx. And which one's going to become the opposite? All right, so let's think which way we're going. It depends if we want to call it clockwise or counterclockwise. For coordinate notation, it would be easier for us to, because it's understood that we're going clockwise. So that means we're going 270 degrees clockwise. So we're going to write it both in words and in the coordinate notation. So we're going to rotate 270 degrees clockwise about the origin. So then coordinate notation, we would write that as R 270, and each of our points is going to be flipped. Which one becomes the opposite? Notice that this is the second quadrant. In the second quadrant, the first coordinate's the opposite. The first one's negative, right? So we need -yx, right? So in coordinate notation, it's going to be R 270, xy goes to -yx. Right, so that means that our points for D prime, F prime, G prime, right, they're not going to be JFK, JHK, HJK, whatever it is, HJK, because we have to do something else. Right, but this is our intermediate figure here, and that's the rotation. So we're going to flip them, make the first one the opposite. So -1, 2, -1, 4, -5, 2. And let's graph that. Right, so -1, 2, -1, 4, and that would be right here, and -5, 2, right here. Well, now that we've graphed it, that intermediate figure, doesn't that make it so much easier to figure out what our transformation is going to be? So this one was D prime, this was F prime, and this was G prime. And I bet you have no trouble figuring out what the translation is. All right, so notice we just have to move every point up 1. Right, so our translation, every point, every x and y coordinate is going to change such that x doesn't change at all, but the y is going to go up 1 unit. And there we go. All right, and so this is the end of Congruence Transformations podcast. We've completed, oh, I wanted to write one other thing. Before, I'm going to go over also the whiteboard practice that goes along with this, but let's write our congruence statement. Since there was a sequence of rigid transformations that maps triangle DFG to triangle HJK, and that is triangle DFG is congruent to triangle HJK. There it is, we did it. And so this is, and I will explain this in class again, but just in case you miss it, you can hear the podcast, you can look at the podcast again and hear the explanation for your whiteboard practice, which will come up any day now. There we go. All right, so I will give this to you on paper. All right, so this is congruence transformations. You're going to use the definition of congruence in terms of rigid motions to determine whether the two figures are congruent and explain your answers. All right, so I've marked in there who's going to be the image and who's going to be the pre-image, right? Because, well, they don't, it's hard, you don't have a statement there for you to know which way it goes. All right, so that way you know which way you're mapping. All right, and now I want to clarify, what does it mean to use the definition of congruence in terms of rigid motions to determine whether the two figures are congruent and explain your answers? What does that mean? It means part A, first of all, tell me if they're congruent or not congruent. You can write it in just like we did over here. Right, it's his turns. There we go. Come on, Paige. Any day now. I really hope. There we go. I get nervous when I see that spinning ball of death. All right. So here we had on the first one here on A, we had a not congruent. You just put a congruent symbol and put a line through it. All right. If you're not congruent, just write the two, match them up the way they're supposed to go together, or as best you can. Right. So here A, B, C, and D, F obviously it goes A with D, B with E, C with F. Right. They have the same shape, but they certainly don't have the same size. All right. And so then this is not congruent. And then if they are congruent, instead, so this is if they're not congruent, you'll write that. And I'm going to erase this later because this is what you'll write if they are congruent. I don't want to save this for all eternity. I just want you to know the directions, right? So you're going to write something like, you're going to write that kind of statement, either a congruent statement or a not congruent statement. That's the first thing. And then the second thing, you have to explain your answer, and as soon as it turns over, I'll tell you what I mean by explain. So if they're congruent, this means that what you need, there has to be a sequence of rigid transformations that maps the pre-image to the image. So if they're congruent, on part B there it says, what transformation maps the pre-image to the image? If they're not congruent, explain or show that no transformation moves the pre-image to the image, or show with measurements that the figures aren't congruent. All right, you need to explain why are they not congruent. On the second pair here, the second set of problems, for each pair of congruent figures, they're already telling you they're congruent. Find a sequence of rigid motions that maps one figure to the other. Give the coordinate notation for the transformations you use. State your transformations, be specific. I'm gonna be very unhappy with you if you tell me rotate, translate, reflect, and that's it. Notice it says coordinate notation. All right, I'll accept words for rotation and reflection if you're still having trouble putting it in coordinate notation, or if it's not x-axis or y-axis. But do not just give me a vague answer. Be specific. Right? So on the second set, it's a sequence of transformations. It may be more than one transformation. It could be that there is a one transformation, but you don't have to worry about doing it in one transformation. I would just do it in two. But in the first set, it's likely that it's only one transformation. And in the first set, you do have to tell me congruent or not congruent. All right, so that's it for this podcast. Bye for now.